Welcome back to Playing Breakout with a Deep Reinforcement Learning, Part 5. So today, if you watched the last video, we coded out the replay memory method, and now we are going to be getting started on the agent class. There's a big part of the training that this class covers. This is the last big stretch of code we're going to have to write, and then the rest is just going to be a few utilities. So stick with me. We are nearing, if not the end, then at least the midpoint of this journey, and we're going to be getting to something really cool soon. So, as usual, we're going to start off with an init method, and this one takes quite a few parameters. So this is going to take a model, a device, which of course we default to CPU. It's going to take epsilon, if I could spell, and we're going to set that to 1.0. It's going to take min epsilon, and to start kind of describing what these are, so obviously the model is going to be our model that this agent is training on. Epsilon in Q-learning is generally used to denote the frequency with which you select a random action. So when you start training, you want it to select a certain number of random actions to begin with, and those random actions are going to give it something to build and learn off of. If you don't, pick X number of random actions, then your agent's going to learn to just sit in one place. If you try coding with a very, very low epsilon, I've had, this agent decide that sitting on the left side of the screen with the paddle was the right way to play Breakout because it occasionally got rewards. And that obviously doesn't work very well. Min epsilon is the lowest level we want epsilon to decay to. So what we're going to do is over time, epsilon is going to slowly go from 1, which is it's a probability. So it's going to go from basically selecting random actions 100% of the time to selecting random actions 10% of the time. And that 10% is how we get the model to continue to try new things instead of just always picking the best action. In machine learning, that's usually referred to as the explore-exploit dilemma, and that is worth doing some reading on by itself. NB warm-up. So that's the number of warm-up steps. We're going to default that to 10,000, and that is the period over which epsilon should decay. I'm going to pass in NB actions, and I'm going to set that to none. I'm doing that on purpose because if someone doesn't pass in a number of actions, I kind of just want this to fail. Because, you should have to set that explicitly. Memory capacity, I'm going to set a default of 10,000. We're going to end up using more than that. Batch size, here this is a good place to drop down to another line. Batch size, we're going to default it to 32. And learning rate, we're going to default it to 5. All right, so your learning rate is measuring how big of a step you want the agent to take every time, how quickly you want it to learn. And, out of the box, you might think, well, if that's how quickly it learns, we would want it to be fairly high. But what that can allow it to do is actually jump erratically from solution to solution, as opposed to slowly building towards the right thing. So you actually want your learning rate to be high enough that it will actually pick up changes and learn, move towards the goal. But if you make it too high, what you'll find is that your agent just isn't learning. It's not trying things out in small enough steps to pick up an optimal policy. So that is our last param. We're going to come down here and start coding these out. So self.memory equals, and this is where we're going to use that replay memory class we talked about. Device equals device. capacity equals memory capacity. Okay, self.model equals model. Self.target model equals copy dot deep copy model dot eval. So what are we doing here? When you're working with Q-learning, you don't always want to use the primary model. You actually want a model, and then you want a model that it can evaluate off of. That's part of the dueling nature of Dueling DQN. This interplay gives the model an anchor to work towards. So it's this model constantly trying to work towards a similar target as this model, and that helps stabilize the training as it goes. I'm probably not explaining that well. It is absolutely worth reading through a theoretical discussion of Dueling DQN. That is not what we're trying to do today. So rolling on, we're going to set self.epsilon equals epsilon, self.min epsilon equals min epsilon. Now let's set our self.epsilon decay. So there's a couple of ways to do this. You could just set a number. So the end formula we're going to do will look something like this. It's going to look like epsilon equals, or sorry, it'll look like self.epsilon equals self.epsilon times self.epsilon decay. And that'll need to be some number. So like if we made this 0.9, then epsilon is going to, reduce by about 10% every time. It's going to get multiplied by 0.9, and it will slowly reduce to min epsilon. So, but I don't want to have to pick that number every time. So this probably isn't a perfect formula, but it's one I found worked close enough for my purposes. So I want epsilon to be 1 minus epsilon minus min epsilon divided by NB warmup. And then we'll wrap all this in quotes. And then we're going to say times 2. And we'll do an n paren out here. So what that's, I did not mean to wrap the 1 minus. That's the part that we don't want to wrap. So what that's going to do, so if epsilon is 1, so this is going to be, we've got 0.9, so the difference between epsilon and min epsilon is going to be 0.9. So right off the bat, that would be 0.9 divided by NB warmup. So the number of steps, between 0.9 and NB warmup times 2, and that's going to end up, and then we subtract all of that from 1, and it is going to give us our decay rate. That'll get pretty close to that NB warmup steps count. Like I said, that formula isn't perfect, but it's gotten close enough for what I wanted to do here. So I'm going to say self.batch size now equals batch size, self.model.to device. So here we're just sending our model to our device. Self.target model.to device, sending our models to our GPU. Self.gamma, that is going to be how much we discount future rewards. Self.nb actions equals nb actions. And then we're going to declare our optimizer. So I generally just default to Atom. It is the best for most use cases, and it's a good place to start. All right, and it's giving us a little error there because we don't have, we are not importing our optimizers. So let's go ahead and get the couple more things from Torch we're going to need. So I'm going to import torch.optim as optim, and we're also going to import torch.nn.functional as f, which is the traditional variable name to use for that. All right. So, and then I like to add a little bit of output just so I know what my program's doing. I'm going to say starting epsilon is self.epsilon. Print epsilon decay. And this is the kind of stuff that for me, yes, I can go look at the values, but when something goes wrong and I'm troubleshooting, it's incredibly helpful to be able to see that, hey, that variables like epsilon got passed all the way through and are, working the way they're intended. All right, so let's start down our path of we've got our init method. That was a long init method. Let's start defining our other methods. So we're going to do get action, and we're going to accept a state, which will be, of course, an image from our environment. And then this is where epsilon comes in. So if torch.rand1, so in other words, if a random number between 0 and 1 is less than self.epsilon, return torch.rand int self.nb actions 1, 1. So in other words, and this is where I appreciate the standard variable names for for machine learning processes, and I will continue to use them. But I do think that things like calling a variable epsilon does make it a little bit harder, especially if you don't come from a math background. You read that and it's just a little bit more challenging to think through what it's there for, what it's doing for you. So it really is just the probability of selecting a random action. That's it. This is the only place. All the times I've said epsilon in this video, this is what it's used for. So if some random number between 0 and 1 is less than whatever epsilon's set to, then we're going to take a random action. Which is what this is doing, giving you a random integer. And then as we slowly shrink this, at 1.0, then a random number between 0 and 1 will always be less. At 0.1, then the random number is 90% of the time going to be more. So that's really all this is. So we're going to say else AV, which is action value, equals self.model state detach. So that's just, hey, we since we didn't take a random action, we're going to pass it to the model, and then we're going to return torch.argmax AV dim equals 1, keep dim equals true. Oop. And what argmax does is it's going to go through and grab the highest value option. So what your model's actually going to return is it's going to return a list of probabilities. So that's going to look something like 0.11, 0.45, 0.22, 0.3. What torch.argmax does is it's going to come through and say, all right, well, out of these 4 arguments, and they're indexed 0 to 3 because it's a 0 index thing. So out of these 4 arguments, which one is the highest probability, has the highest reward? So it would say, well, 0.45 looks like the highest reward, highest probability. So I'm going to return a 1 because index 0, 1. So this will return action 1. So this is a random thing under NB actions. This is what action does my model return. All right. Now we're on to the train method. This is going to be a long one. So we're just going to go ahead and dive in here and start coding. So def train, env, epochs. I've also seen people use episodes here, and this is how many iterations we're going to train for. First off, you probably want some kind of stats. You could totally do this whole model and never pick up any statistics, but it is incredibly useful to see how your model is doing over time, over and above what you can just print out to the console. So the things I'm going to track are returns, and we're doing these as a dictionary of lists specifically, AVG returns, and epsilon checkpoint. And anyone who is actually good at dealing with data is probably going to say I'm doing this wrong, and they're probably right. Again, this is how I solve the problem. It doesn't have to be how you solve the problem. I am going to, we're going to set up a plotter to plot some of this data. For now, I'm just going to go ahead and create the file so we can reference a method. I'm going to call it plot, and we're just going to say class live plot and put a pass in here so that it doesn't complain at us. Save that, and then come back over to my agent, and we're going to say from plot import live plot. At least we've got the structure there, and then I can declare my plotter. So plotter equals live plot, and doesn't matter that it doesn't do anything right now. So we're going to say for epoch in range 1 to epochs plus 1, and this is to make sure we're not at a 0th epoch. We're going to say state equals env.reset. So reset in Python gem is basically what's going to obviously reset the environment, take it back to no lives lost, score of 0, all that fun stuff for each iteration. We're going to set done equals false. So right off the bat we're not done, and EP return equals 0. All right, while not done, so while the episode has not been completed, we're going to say action equals self.getAction state. See, once you've built a lot of the supporting classes and methods, a lot of this does start to be a little bit simpler. We don't have to think about how to get action, just call get action and pass it the right values. We're going to take a step in the environment, so that's going to be next state, reward, done, info equals env.step. And those are just the standard values that you return from gym. And then we're going to insert that value into memory. All right, and again, you'll notice I am inserting a list here of state, action, reward, done, and next state. So it's going to have all of those available for each memory step. So here we get to the actual training part, and this really is what is training the model. So we're going to say if self.memory.can sample self.batch size. So remember, we wrote that can sample method to make sure that it had at least 10 times the batch size in there. We're going to pull state B, action B, reward B, done B, and next state. Why are all these called B? Well, because they're batches. So what we should end up with is we should end up with a series of batches of all of the states, all the actions, all the rewards, all the dones, all the next states. That's what this zip star.batch is doing for us. It's taking those samples, it's zipping them together, and it's letting us pull them as these unpacked as these variables instead of just having to circle through them one by one. So, and the first time I saw this format, it threw me a little bit until I realized that the model is perfectly capable of processing a large batch of states. It doesn't have to read them one by one. You can pass in a batch of 30 or 50 or 100 or whatever you want them to be and get that information back. So it speeds up training drastically to do these things in batches. All right. So we're going to say self.memory.sample. All right, and then we get into the Q states. So QSAB is going to be the Q state action for the state B, action B. So we're going to say self.model. And this is another one of those places where it is really worth going and reading into the theory. I'm not going to try to explain it in full in this video because, again, that is not our purpose. One, action B. Next QSAB. Self.target model. So here we're getting the predictions of the target model on the next state. So what does it think the next state's value is? Here we're just doing a little bit of processing. Not the next state's value. This is what it thinks the appropriate action is for the next state. So here we're going to say torch.max. Next QSAB, again, dim equals -1, keep dim equals true. We're going to grab the 0th element. Target B equals reward B plus, and I'm using a tilde here to negate the value of done. And the reason I'm doing that is if done is a 1, if done is true, then the next state value is obviously, there is no next state value. So that's what we're doing here. That's what that does for us. Self.gamma, so that's how much we are discounting future states times next QSAB. All right, we're getting to the end. So we're going to declare loss equals f.mse loss, QSA B, target B. So what we're doing here is we are comparing the differences between between its prediction and then the value based on the actual rewards here. Next, we're going to say self.model.zeroGrad, and that basically zeroes out the gradients so we can go through and update them. Loss.backward, and this is the actual back propagation step combined with self.optimizer.step. All right, So that is the actual training block. That is one of the most important pieces of this code base. Is worth looking at and making sure you got that right. So we're going to say state equals next state. So why are we doing this? Well, we did the training. Now we need to go ahead and make, state the value of whatever we got back here. And we're going to add our rewards, reward.item to episode reward. Oh, I missed a thing there. Plus equals. So basically plus equals is EP is a shorthand for writing EP return equals EP return plus reward.item. And then we can break out of our while loop. And we can go ahead and say stats returns dot append EP return. Okay. Now finally we're going to get into, so at this point this thing would sit here and churn and learn, but we would be missing some of our output, some of our other information, and we would not be saving the model. So we're going to be adding just a little bit more here. We're also going to be saying, so this is still inside of our while not done. We're going to be saying if self.epsilon, so now we need to do our epsilon decay, is greater than self.min epsilon. So I misspoke a moment ago. You do need some of these things to learn effectively. Then we're going to say self.epsilon equals self.epsilon star dot epsilon decay. So if it's greater than self epsilon, we're going to go ahead and multiply it by epsilon decay. And then these are purely arbitrary. I wanted to do checkpoints and write statistics and train the model every so often. For me, what that is every 10 to save the model and push some information to the plot. So what I'm doing here is I'm basically saying if the epoch number modulus 10, so if it's divided by 10 and that equals 0, this is a great way just to say, yes, I'm on 100, I'm on 110, 120, 130. Then I want to go ahead and say self.model.save the model. I'm just going to give myself a little spacing there. Average returns. Oh, we may not have declared an average returns. Let's see where that should have been. Okay, yeah, this is where we want it. Average returns equals np.mean stats returns negative 100. So we want to grab the last 100 items of returns. We also need to come in here and import numpy as np. That is going to be required. That's why it's giving us a little error there. So, all right, so we're taking the average returns over the last 100. So you could just plot returns directly. What I found in playing with this was that there's so much data as you train this for a million plus epochs that it just turns the graph into a crazy scribble if you try to just plot everything that comes through. So the way I did it is I did a combination of just grabbing the last 100 values and then only updating the graph with one data point for every 10 10 items here. So that's where we're doing this. We're going to say stats. Oh, I did that wrong. can say stats avg returns dot append average returns stats epsilon checkpoint dot append self dot epsilon. And this was just, I found it very useful to be able to see where epsilon was at as it showed its returns, just so I could see, was I getting high returns with high epsilon or only seeing returns once epsilon had dropped. This was just really, really useful for me while I was working on it. If, and then this is just printing out some, information to the screen as we train. So I'm going to say if stats returns is greater than 100, then f epoch. I'm going to give it my epoch and say average return np.mean stats. Actually, I basically want this value right here. And I lost my curly brace there. All right. Epsilon self.epsilon. You can probably tell by now I'm big on useful output as we go here. Else, and then I'm just going to steal this. And we're going to turn it into episode return same thing except -1. So basically for the first 100 iterations we're just going to return the episode return, and then after 100 iterations we're going to start, because we have 100, we're going to start returning the average over the last 100 after we have that data. All right, and then we're going to come back in line with these if statements, and we're going to do a couple more things. We're going to say if epoch percent 100 equals 0, self.target model.loadState dict self.model.stateDict. So every so often you have to keep the target model lined up with the the main model, so it's effectively learning in hops. And also every 100 steps we're going to say plotter.update plot stats. And there's not an update plot method, so it may error on us. Let's go ahead and come over here and just say def update plot, and we'll do another pass. We're going to implement that in the next video. All right, and then something I like to do as well, I want to say if epoch, this is not strictly necessary, but it is useful. If epoch by 1,000 is 0, then save the model. And I'm going to put that in models/model iter. And this is not a file that we'll ever use directly in the code. The reason I started saving these off is I would find that that maybe I got really good performance around 600,000 epochs, and then something happened and it tanked. I could go in and copy this in as the main model file and either restart training from the good point, maybe with some tweaks, or I could look at this one and then look at something 10,000 epochs later and see, what the behavior was that the actual model was doing, and not just the scores. So, did it learn to stick to one side? Did it learn to do, like, why? Why was it failing? So this was a useful step for me. This whole project will run just fine without any of that code. So, and then finally, we are just going to make sure we're all nice and lined up here, and we are going to return stats. So, and I think that is probably a really good place to stop. In the next iteration of our video series here, we're going to build out the test method of our agent model, so the method that'll let you just run the agent and see how it's doing, and then we'll probably also put together the plotter code, and after that we are just a few more lines of code away from seeing this thing run. So I will see you next time.